When do we cover divergence?
When? Sometime in our future. Okay. Yeah, I'm not. You can see when the pacing gets us to that section. Oh. All right, guys. Anybody not get that handout from section 14.7? The one about interpretation of second derivatives. Second derivatives test. Kind of did this in the class together. Oh, right there.
Pop over my pop it.
I covered my mouth.
Ew. This person is. We're gonna build a wall.
Build a wall.
Don't even.
Make her pay for it.
We're gonna make this table great again.
Why don't you look up my book in class?
Alright, guys, so any questions? I think there's one thing we could do related to a question a minute ago, but any questions from homework stuff?
Could you just hit on that one where where was it? 62. Still have no idea how to do that.
Oh yeah. So let's take a look at 62. So there's a few things to kind of get through. If you look at number 62, this is section 14.6, page 999. 999. Pyramids in the first octant. So you have some surface x, y, z equals 1. That sounds like it's probably a weird looking surface.
Yes.
Yeah.
And it says the pyramids created by the tangent planes to this in the first octant. Yeah, cool. So, how do you find the tangent planes to a surface? I mean, that's where you can start.
Normal vector. You could use the formula. I mean,
It's crazy. So, did you get the equations? But the rough thing, of course, is it's not at a specific point. It's at some arbitrary point on the surface, right? Okay. Okay. I mean, so step one is I would find equations for the tangent planes. To the surface at some almost completely arbitrary point. That would be like 1 over xy for z, right?
Yeah, so you end up getting a tangent plane. And then as you scoot the tangent plane around, the 3 points at the intersecting axes move around. But how do you prove that no matter where...
So now, it's good. I mean, it's beautiful. And there was an earlier picture, I can't remember where we found it, somewhere in the book. There's a nice picture of, it's a little triangle shape dealy. Let's see if we can do this. So in the first octant, get out of there. Something like this here. And then there's the plane. But, I mean, this represents a pyramid, believe it or not, if I filled it into the corner being the origin. So it's cut off by all of the xz plane, the yz plane, the xy plane. It's in the first octant, right? So you can imagine this is the base of the pyramid. One way to look at it is just to let it stand the way it is. Another thing you need eventually in one of these steps is the volume of a pyramid. And the volume of any repeated shape. So if I repeat a square, if I repeat it, the volume with the area of the base, which we call big ass B, or I call it big ass B, other people just call it capital B, times the height, times the number of times that square is repeated. And then if I make a pyramid out of this, which for me, that's pretty, look at that. A beautiful pyramid. All a pyramid is taking all the corners of a base and connecting them to a single point. It doesn't even matter where that point is. I can move that point around. It's going to have the same volume. It's going to be 1/3 the volume of what it was cut out of.
Don't you have to half that again though, because we have a 3-pointed pyramid?
So now, no. So the picture doesn't go along with this because the base of this one is going to be a triangle. I like it. But it's still the same equation because the area of the base is going to be the area of a triangle. You guys kind of, I like it. So what you're going to need to do, if I gave you the equation of a plane, how would you find this point?
X and Z equals 0.
X and Z equals 0, right? How do you find any intercept? Make all the other letters 0. Yes, sir.
That one, Z can never be 0. In that arbitrary point.
Oh, yeah. If I let X and Y be anything they want to be, then Z has to be 1 over XY, right? But again, I need to get the equation of the tangent plane first. It doesn't matter what my surface is doing for this problem except to create the tangent planes. All that matters is what the tangent planes are doing. You guys semi with me? So I could have a surface that never intersects any of the axes, but I don't care because my tangent plane will at some point. All right, maybe. You guys love this problem, I can tell. Yes, sir.
I'm sorry, what is it asking us to do?
It's trying to find the volume, show the volume that is always the same volume.
Okay.
So if you can get expressions for these points based off of your equation of the tangent plane is going to look possibly gross because it's not going to be based on a specific point. It's going to be based on any point on the surface. So you got to get the equation of a tangent plane. But how do you find the intercepts once you have the equation of a plane? You just make, if you want the x-intercept, you make the y and z 0.
But that's not the hard part.
If you had the gradient and then you multiplied it by x minus x naught is any arbitrary points, wouldn't that just be x minus x, which would just be 0?
Where are we? Sorry.
Disappears. If you got the equation for the tangent plane, you had the gradient, that's your normal vector, so you took that and multiplied that by x minus x naught. Since it's arbitrary, wouldn't that just be x minus x, which is...
No. It is arbitrary, but it is specific for a certain plane. I mean, we have to be past this point. I'm going to get an expression that represents all possible tangent planes to all possible points, right? But for any specific tangent plane, I'm not sure exactly. I got to construct that equation first. So that sounds like you're in the middle of constructing the tangent plane. What was I going to say? Right here. So let's say this is obviously y, this is obviously x, and this is z. Let's just call those values what they are. So what's the area of this triangle base?
1/2.
The beautiful thing about that triangle is it's a right triangle, so I know that the height is like the x-axis and the base is the y-axis, or vice versa. Who cares?
1/2 x, y, z.
No. The area of this base is 1/2 xy.
Times 1/3.
So that's big ass B, right? So I can get an equation for, so big ass B will be 1/2 xy, and then what's the height? Z. So I got an equation for the... Now, do you notice something?
It looks very similar to...
Yes! Actually, I didn't want to go this far, but I couldn't stop myself. I didn't know if anybody would actually just sit down and actually try to construct the formula directly.
Oh, I did that, but...
Now, what does it say? The surface, what's true about any point on the surface? Any point on the surface, what's true?
Equals 1.
XYZ equals 1. So the volume will be 1/6.
Oh, I thought you wanted us to prove that if you hold the others constant and move one in relation to each one, it always ends up...
Well, this is the shortcut. I didn't want to show you this, but I couldn't stop myself. But well, I'll see if you guys, anybody tries to keep going the full-blooded way. I'm curious. Any point on the surface meets this requirement. So those 3 points in particular are on the tangent plane. Now, do they meet this requirement though? There is a point, so you got to be careful. I don't think this is maybe the best shortcut because it's not necessarily true for points on the tangent plane, but it is true for that one point that the plane is tangent to. So you maybe can't extend it that far. So you should probably keep doing this. I like it, but that's interesting. That's an interesting connection there. But those points are not on the surface. Those points are where? They're on the tangent plane. I like it. So they don't necessarily follow what the surface wants to do. Yeah, my brain thought that might be a shortcut, but not quite, because they're on the tangent plane, not the surface itself. I was hopeful for a second to find a shortcut. But you just got to keep going with this. Yeah, too bad. But I mean, once you get an expression for the x-intercept, the y-intercept, the z-intercept, you plug them into this, and somehow it's going to come out to be independent of point. Yeah. Hopeful.
So you're saying the point doesn't matter?
That's their point, is that no matter what point you pick on the surface to construct a tangent plane out of, the volume is going to come out the same at the end of that pyramid you created.
So what do I need to plug into the volume to get some?
A lot of stuff. You got a lot of steps. This problem, I love this problem. If this is the only problem giving you trouble in this section, you're doing pretty good, because this problem is kind of long. Yeah.
Number 58.
Oh, 58. Okay, all right. That's all I'm going to say about that one. Yes, sir.
Just kind of recapping, you can only use the gradient if you use the as the normal vector of the tangent plane. If you do the step up the dimension thing, and it's a 3-part gradient, right?
Yeah. I mean, that's the
you can't do-
process we use to figure out the equation for it, right?
Okay.
Doesn't mean that you actually have to do that. I mean, you have to set it up so you can
Well,
find
yeah,
the correct gradient. Sure.
But you can't use just an XY gradient.
Oh, I see.
Find the tangent plane.
No. Cool. All right. Anything else from homework stuff? Oh, I'm sorry. Which one was it, Jesse?
58.
58. Oh yeah. This sounds neat. Any problem that starts with show that every I remember that feeling. Show that every normal line. Okay, first off, what the hell's a normal line? This is 58 in the same section. Show that every normal line to the sphere passes through the center. So I'm supposed to show every normal line to the sphere. And if you think about it, what does the word normal mean in the context of this course?
Perpendicular.
So it makes sense that, and we did discuss a little bit about, I can't remember exactly how we said it, but circle or sphere is the only thing where it actually is pointing directly in towards the center. So we're sort of proving this point. So the normal line must be perpendicular to the tangent line, right? And this is one of those, show that every normal line, so you're just going to have to pick some arbitrary point, x naught, y naught, z naught, or ABC, if you don't like all the knots, right? Construct the equation of the normal line at the point ABC on the sphere. Of course, C is not anything it wants to be. It has to be on the sphere. That might be helping, might not be helping. So I want to construct the equation of a normal line to the sphere at any point. So number one is, how do you construct the equation of a normal line? Right? And then number two is, once you get that equation constructed, how do you show that it goes through the center? Well, that shouldn't be too hard. How do you show that any line goes through the origin? It doesn't have like in 2 dimensions, it won't have a constant attached to it. So if I have a line whose equation is this, does that go through the origin? Does that line go through the origin? Yes, it does. There's no plus b, right? There's no plus r naught. It must go through the origin, because if t is 0, what point is it at? 0, 0, 0. So once you construct the equation of this normal line, somehow it's got to be looking like this, possibly, depending on the way you do it, or it just shouldn't have no constant added on. All right, maybe. Okay. Does anybody try that problem yet? A few of you guys? All right. All right, all right. Where do they talk about normal lines, just to kind of help you guys out? Normal line, here we go. Yeah, right there. Blah, 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 blah. Here. Yeah, bottom of page 994. That's going to be a huge help to you. I mean, this is, for you guys, if any of you are math majors, you are going to want to appreciate the hell out of the time that the book still has examples, right? Because you're going to get to a point, trust me, where you're going to have these little tiny books that still cost hundreds of bucks, and there's theory, and then problems, and you're like, oh, what the hell happened? So look back at the examples, look at keywords, normal line, look up where it is, where was it first introduced, see if they have an example of how it's constructed. I mean, this is what you want to do for yourself, right? And if the book don't say shit about it, then you got YouTube, you got me, you got tutors, you got everybody. This is where you got to start bringing in and understanding what all your resources are. Actually, this isn't when. Should have happened a few classes back. So, but if you haven't done it yet, you want to do it now. Okay. Anything else from anything else in the homework? Maybe we get an example of let's do this one. This is from section 14.7. This should sound familiar. Then we'll get into chapter 15.
I actually got a question if you can do that after.
From 14.7?
Yeah.
Which one?
It's number 16.
All right, let's take a look. 16, let's build up to this word problem. So they give you this here. Sure. It doesn't matter, but you can just make them the same as theirs. Okay, so X, Y, E to all that stuff up there. And they say find the max and min, or identify if it's a saddle point, find the critical points. Blah, blah, blah. So how do I find the critical points? Yeah. So this feels very familiar, even though we have several variables going on. Now what's F sub X going to involve? Well, yes, product rule, I like it. All right, so the first part would be derivative of X, I'll do that. Plus, cut this guy off here. This isn't too bad. And again, you can always, so XY stays alone, and then you're going to take the derivative of this, which is itself, times the derivative of the inside. Where? I'm sorry.
At the beginning, wouldn't that be negative x squared?
It's 2x over 2.
Why? What happened? No, I took the derivative of this.
Yeah, I mean, in this part, x, that would be negative x squared y e to the right.
Why? What's happening?
Why? Because it's negative x.
Oh, we haven't done this derivative yet. Have you done this derivative already?
Yeah.
Okay, I haven't done it yet. Yeah. I want to make sure everybody understands where everything's coming from. So leave this alone. Derivative of this is itself times the derivative of the inside. Right? So again, if you need to, you can certainly write it all out for yourself prior, or even better, d by dx. Is that cool? I don't know where the trouble. Were you able to get the partial derivatives figured out?
Yeah, that's what I have trouble with it.
All right. So then what happens there? What do you get here? Negative x. I like it. Right, negative 2x over 2? Yes, sir.
How do you pick your critical points after you do all these derivatives? Because I'm not really sure how to combine the points that I got. Because, I mean, for this one, where it's equal to 0 is when y is equal to 0 and when x is equal to plus or minus 1.
So that gives you points to plug into the other derivative, because that's the only points where it could possibly have critical points. So if I figure out where fx is 0, I'm finding those components, which are the only possible parts of the answers, because that's where fx is 0. I like it. So then you plug those points into the second one. So it's not as wide open as it sounds like it could be. So let's see. What can we do with this beautifulness? We can take out a y(e) to the negative x squared plus y squared over 2. We can take that out. And what am I left with? 1 minus x squared. Well, that looks kick-ass. Right? This is what kills people. This is what makes me so sad. And I'm not... factoring is so unbelievably important. And it seems so contrived when you first learn it, because if I say, how do you factor this? Well, that's easy, but then all I got to do is make that a 7, and then ha ha ha, So when you first learn factoring, it's like, well, what good is it? You got to make sure that it works out. But you should know by now, when you take derivatives, the symmetry inside of the derivatives you're taking results in these things that are factorable. I mean, it happens. We've seen it happen. So factoring happens a lot more often than you would possibly think when you first learned it. If you really paid attention, it's like, always got to be careful about that number. It makes that one number, and then they do this shit. Hello, But we should know by now that it happens in the process. So yeah, when is this equal to 0? When y is 0? This is never 0. Doesn't give me shit. And then, or when x equals plus or minus 1. Now when I do fy, I'm going to use those with fy. I like it.
So use them how? So would your only two critical points be 0, 1, and 0, negative 1? Or
No. This is its own thing. This is its own thing. This is its own thing at the moment. Stay with me. This is not the best problem to do this, because the derivatives are just kind of gross. Can we... I don't want to do this problem for you. Does that help you out?
So then you're going to get y, the derivative of y, and
Yes.
plug in the 0, and then you're going to find an x component for the what you solve for y.
Yes. Cool. I don't know if I want to find fy for this
And
thing.
then you find your critical points.
Yeah. So let's do one. Let's do another one. That's not as disgusting, and that's not maybe assigned. So I'll feel a little better. And just show you all the way out. Sure. Let's see. I want something where... Yeah, let's see. So here, let's see. This is number 11. Plus 3xy squared, yeah. fx, 3x squared minus 3 plus 3y squared. Is that cool?
Yes.
So where's this equal to 0? This is going to be interesting. This might be a little too interesting. When x squared plus y squared equals 1, do you guys see that?
Yes.
So it's every point on that circle. All right, so sometimes I'll get points or coordinates, components of a point, and sometimes I'll get expressions, relationships. Every point on this circle, the outputs for that are on, like this is where the x derivative is 0. So if I put into this function any points that are on this circle as an input, it's going to end up at a point where if I move in the x direction from there, it doesn't change, right? Fx is 0. So that's what that means. Any point on the circle, if I use it as an input for this function, I'm going to be sitting somewhere where if I look in the x direction, it's flat for that immediate time. Right? That's what that means, because I said it equals 0. Fy is just going to be what? 6xy. And when is that equal to 0?
X or Y equals 0.
If x equals 0 or y equals 0. I like it. So for x equal to 0,
Y is 1.
yeah, so if x equals 0, then y from this one,
Plus or minus.
y squared equals 1, so y equals...
Plus or minus.
Now really, this is getting directly to your point. These came from using this. Therefore, these points are very well defined. These came from this value of x. So that's the x that goes with these y's. If y is 0, then x is going to be plus or minus 1. So then this is going to be plus or minus 1, 0.
So for this question, we should get 6 critical.
Possibly. I mean, it might turn out that some of these don't ever make fy 0 at the same time. Does that make sense? So here, it's more restrictive to find critical points. Maybe. Now, obviously, I'm leaving out one thing because these functions don't have any problems on their domain. Their domains are everything. Is there anywhere that's undefined? But you can't forget that. If there's somewhere where the function's undefined, you have to include that as a critical point. I like it. Just like back in 1A. But I understand your question, because if you get here and you get all these, is the point 0, 0 a part of this at all? No. I like it, because when x was 0, I didn't get 0 for y. When y was 0, I didn't get 0 for x from the other dude. So therefore, no.
So those that x and y value you're plugging back into the circle?
Yeah, this is now a system of equations. I've got this equation, and then I've got this equation, right? Which really leads to these conditions. Maybe. You can see that 0, 0 would not be a part of this because it doesn't even work in this guy. You can't even make fx 0 on its own. I like it, maybe. But there should be no question about how do I put together my points, because that coordinate made these coordinates, therefore those are the points. They go together. When this is true, this is true. That's the meaning behind a point. I like it. All right, let's do one, unless there's another specific question, I want to do one word problem. Yes?
Wait a minute. Is it 4 possible or 6 possible?
No. So Mike was trying to saying
that one,
there
okay.
is the possibility of getting 6 separate points here, right?
For that one.
Yeah, for this
Not
one.
that one.
This one there were 4. I like it. There could be 6 because this could have 1, but each one of these could have 2. Whoa, who knows? It all depends on the other guy. I like it, but who cares? Why do you want to know ahead of time? Just get there and find out. All right? Part of it is that. All right, let's do this. I want to do number 53. I've forgotten how to work a towel. It's a bad sign. All right. 53 should sound familiar. Good old open top cardboard box. This needs to have a volume of 32,000 cc's. And I want to minimize the amount of cardboard used. Well, that's not too bad. But I'm always surprised about how much trouble there still is just constructing equations from a given situation. We have to be decent at modeling situations with variables. That's why we created variables, so we can do shit to something I don't know. I don't know how much Bob makes. Let's call it B, and then I can do stuff to B, and then I can set up equations with relationships with B, and I can do stuff. So what the hell? This is all it gives me. Find the dimensions that minimize the amount of material. It doesn't say anything else. The amount of cardboard used. Gonna make this beautiful box. Now it's cardboard. Yeah, I like it. So I can call this L, W, and H. Sure.
This is just all sides, top, bottom. Same.
The top it's open, so there's no top. We're not going to waste any cardboard on the top.
So B is equal to L.
Screw that. If these people want a top, they can do their own thing. So obviously,
Minimize the cardboard.
so this is the thing that yes,
You're just making a function, right?
yes, but what function am I making?
Surface
Length
area.
times width.
Surface area function. How do I know I want to make a surface area function?
Minimize the cardboard.
I want to minimize the amount of cardboard, which is the surface area of this thing. So, for example, I don't know, some of you guys had me for Calc 180. You might remember the problem about the different types of fencing I used on the different, So I said minimize the cost, and everybody made a perimeter function and minimize the perimeter. That's never going to work. It's never going to answer your question because I wanted to minimize the cost, minimize the blank. So you got to make a function that represents blank.